Hey everyone, today we're looking into stars, and not just their glow, their size, or their age, but something else, something invisible that flows out from them like breath on a winter morning. It's called space weather, though it's not like the weather you feel through your bedroom window or see in the sky above your house. There's no rain up here, no clouds that pour, but there are storms and wind and flares and calm stretches too, quiet as deep sleep. So go ahead and lean back, let yourself drift. I'll handle the steering. There's no rush where we're going. Imagine this. We're hovering just above the surface of a golden star. It's huge, not just big, but impossibly, stretchingly vast. Below us, the surface churns like a pot of thick, glowing soup. Bright loops of fire rise up and fall back in, and from every part of it, even the dark little patches that look like bruises, a constant stream of invisible particles is spilling outward. You can't see it with your eyes, but if you hold out your hand, you can almost feel it brushing past your skin. This is the solar wind, not a wind of air, but of tiny, tiny pieces flung away from the star at high speed. Some of these will drift for millions of years. Others will crash into things, like dust hitting a windshield. Every star does this. It's like they're always breathing out. Now picture yourself turning, slowly, as we drift back from the star's surface. That light gets softer behind us, not because it's growing dimmer, but because the solar wind is what we're watching now. It moves in every direction at once, filling the space around us like invisible fog. There are times when it's steady, a soft stream, like a quiet tide that never stops. But sometimes, this calm is broken. Deep inside the star, something shifts, magnetic ropes tangle and snap, and in that moment, a flare explodes outward. Light, heat, and wind surge off the surface like a cannon blast. We feel it here, even far away. The stream thickens. Particles pour past us in fast, bright waves. And if you're quiet, you might even hear it, a low, whispering crackle in the emptiness. Let's drift sideways now, away from the star but still in its wind. You might notice little ripples like gentle waves in an ocean of things too small to see. These ripples come from changes in the star's surface. Sometimes, dark patches called sunspots appear, swirling and cooler than their surroundings. Around them, storms brew, building tension like thunderclouds before a summer storm. And then snap. A burst of energy leaps up. It's not fire like we know it. It's something more sudden, more electric. These are solar flares, and when they erupt, they fling material into space. Big ones can send shockwaves racing through the solar wind. Reach out now. Feel the sudden pressure in the current as one of those shockwaves brushes past us. It's subtle, but it's there, a push, like a ripple from a distant splash. These waves move faster than the regular solar wind, and when they pass through it, they stir everything up. Space weather isn't just about speed, but about change, the way things shift, push, crash, and smooth out again. Now, follow me. We're heading toward a planet that's sitting quietly in this solar breeze. Its sky looks blue from the surface, but from out here, it's wrapped in a shell, a magnetic bubble that shields it from most of the wind. This is Earth, and its magnetic field is like an invisible umbrella. Most of the time, the solar wind flows around it, splitting and sliding off to either side. But when storms come, strong enough, fast enough, they press in, and then something amazing happens. The wind squeezes the bubble. It bends and shudders. Energy builds at the edges, and some of it flows along the lines of the planet's magnetic field, down toward the poles. There, it sparks the sky into color. Maybe you've seen it: green, pink, sometimes purple or red flickering lights that dance and curl above the north and south poles. That's the aurora, and it's the most visible part of space weather from Earth. Listen closely. Can you hear the soft shimmer of those lights? They don't really make sound, but if they did, I imagine they'd hum like distant chimes, moving slowly in great arcs. The particles that cause them come from the sun, carried in the wind, slipping past Earth's defenses in just the right places. It's a kind of cosmic conversation. The sun sends out signals, and Earth answers in light. But Earth isn't the only planet that responds this way. Jupiter has its own magnetic shield, far larger and stronger than Earth's. When the solar wind hits it, massive auroras bloom around its poles. They're invisible to the human eye, mostly ultraviolet, but they're bigger than Earth itself. Saturn has them too, as does Uranus, and even Neptune. The farther we go, the colder it gets. But the sky still dances. Space weather travels far. Let's drift a little beyond now, out past the familiar planets, into the darker reaches where the wind slows down. It's still moving, but thinner, stretched like taffy as it reaches toward the edge of the sun's influence. This is the heliosphere, the giant bubble of solar wind that surrounds the entire solar system. It's not solid, it's not visible, but it's there, like the breath of the sun filling a balloon. And at the edge, where this wind meets the interstellar space beyond, it starts to slow and pile up, like a river meeting the sea. Touch the edge here. It's quiet, still moving but hushed. This boundary shifts depending on how strong the sun's wind is at the time. Sometimes it pushes out a little farther, sometimes it pulls in. But always, it forms a border, a kind of frontier between the space shaped by our star and the space shaped by all the others. And speaking of others, out here, if we look far enough, we can see the faint glows of distant stars, each with their own space weather, each sending out their own winds, carving their own bubbles, stirring up their own storms. What we've seen around our sun, the flares, the winds, the auroras, those aren't just ours. They're everywhere. Billions of stars, billions of breaths. Let's float in silence for a moment and watch it all. The slow streams, the fast blasts, the flickering lights. This is the weather of space. Wild, invisible, ancient. Not random, but always changing. Not violent exactly, but full of power. And it touches everything. Now we can steer towards something smaller, a little satellite, orbiting Earth like a patient sentry. Its panels stretch wide, catching sunlight. But when space weather grows strong during one of those solar storms, the satellite shudders. The particles strike its surface. Its circuits feel the jolt. Too strong, and it might fail. That's part of space weather too, how it affects what we build. Down on Earth, we're not untouched either. Power grids can hum, wires can carry strange currents. Signals from GPS satellites might twist and wobble. It's rare, but it happens. The sun sneezes, and our machines catch it. Look there, just above the curve of Earth's blue edge, another satellite, smaller this time. It's part of a whole group, like a flock of quiet birds gliding endlessly above the clouds. Each one is watching, listening, measuring the wind of space. They're built not just to look down at Earth, but to look out, sensing when the sun's breath grows faster, rougher, more chaotic. These silent machines are our early warnings. They catch the first signs of storms that start 93 million miles away, giving us hours, sometimes only minutes, to brace for what's coming. A flash of radiation, a burst of particles, a sudden squeeze of the magnetic shield around our world. And even though we're safe below layers of atmosphere and magnetism, we still feel the ripple in our technology, our power lines, our navigation systems, our high-flying aircraft. Space weather isn't just out there, it finds ways in. Now let's drift down, gently, toward the night side of the planet. Watch the lights sparkle below cities glowing in the dark like constellations flipped upside down. But near the poles, something even more beautiful appears. The auroras. Look, a curtain of green fluttering across the sky, shifting, waving, then fading and glowing again. Then purple, then red. It's like a watercolor painting that never dries. This is the Earth's reply to space weather, not with fear or damage, but with light. These lights come from charged particles spiraling down magnetic field lines, colliding with gases high in the atmosphere and turning invisible energy into visible beauty. You and I, we can just sit here and watch. No rush, just color and sky and the quiet background hum of a planet responding to its star. Sometimes, though, these storms are more than beautiful. Sometimes they're strong enough to reach deep into our systems. Back in 1989, a storm knocked out power in Quebec, millions of people without electricity for hours, all from an invisible gust of wind that started on the sun. And farther back, in 1859, there was a storm so massive it lit up the sky across the globe. Telegraph systems sparked, even caught fire. It's called the Carrington event, and if that happened today, it could affect satellites, power grids, even internet cables stretched across the sea floor, all from a single blast of energy flung across space. Let's rise back up now, away from Earth, higher and farther until the planet becomes a blue-white marble again. See how the solar wind flows past it, bending around the magnetic field like water around a stone. But Earth's not the only stone in this stream. Let's drift outward, past the moon silent, cratered, without a magnetic shield to protect it. Here, space weather hits full force. Each particle that strikes the surface leaves its mark, slowly weathering the moon's face. It has no atmosphere to cushion the blow. That's why the dust here is so sharp, like glass. And those tiny, tiny particles from the sun, they embed themselves in the soil, changing it slowly over time. Even the rocks up here have felt space weather, and they tell the story of solar storms that happened thousands, even millions of years ago. Keep drifting. Ahead of us now is Mars red, dusty, quiet. It once had a thicker atmosphere, maybe even water flowing on its surface. But over time, space weather chipped it away. Without a strong magnetic field, the solar wind gradually stripped the air, like wind blowing dust off an old map. Some of that air is still escaping now, right before our eyes. If you look closely, you can see faint wisps lifting from the upper atmosphere, drawn out into space by the sun's persistent breath. It's like watching a memory fade slow, beautiful, and sad. And yet, in this slow loss, there's discovery. By studying how space weather affects Mars, we understand more about our own world and what could happen in the future. Now, tilt gently with me, we're turning toward the sun again, but from a different angle. See that huge loop arcing off the surface? That's a prominence, a towering ribbon of hot gas, held up by tangled magnetic fields. These can stretch hundreds of thousands of miles into space, hovering for days or weeks before collapsing or snapping loose. And when they do, if the timing is just right, they can send a giant cloud of solar particles straight toward us. That's what we call a coronal mass ejection, or CME, but we won't worry about the label. Just know it's like a solar sneeze, sudden and full of energy. When one of those reaches Earth, it can compress the magnetic field, stir up auroras, and rattle satellites and radios. It's the most powerful kind of space weather we see. Feel the invisible surge as one of those ejections passes by. It's not fire, it's not a blast like thunder, it's more like pressure. An invisible rolling tide of particles and fields, passing through everything in its path. We're lucky, in a way. Earth's magnetic shield takes the brunt of it. But this is why we watch the sun so closely, why we study its surface, its loops, its winds. It's not to predict disasters, but to understand the rhythm of the sky. The sun breathes, flares, calms. It's alive, in a way that stars are not with thought, but with motion and force. And all of that motion shapes the space around us. Let's go even farther now, past the orbit of Mars, past the asteroid belt, where rocks tumble in quiet loops between worlds. Even here, space weather has a role. Some of these rocks are ancient, untouched for billions of years, but some have been darkened, cracked, shaped by steady streams of particles, a slow erosion done by the softest touch in the galaxy. And farther still, past Jupiter, we reach regions where the sun's influence grows faint but still present. Here, the solar wind thins, stretched over huge distances, but it still carries news from the star at the center. It still carries energy. Now picture this. 2 tiny spacecraft, Voyager 1 and 2, launched decades ago, still drifting outward. They've passed the edge of the heliosphere now, out into true interstellar space. But even here, the traces of space weather remain. Voyager still detects particles, still hears the whispers of solar storms as they ripple through space. The sun may seem far, but its weather reaches farther than we ever imagine. Let's hover beside Voyager 1 for a moment. It's quiet. The instruments are still working, still sending messages home, though faint and slow. This little craft has been touched by every kind of space, weather, solar wind, flares, radiation, and yet it moves onward, a tiny messenger in the vastness. It tells us the edge isn't the end, just another place to learn. Space weather is more than solar flares and wind. It's a story of connection, of how stars speak to planets, how invisible forces shape atmospheres, surfaces, even histories. And in that story, we're not just observers, we're part of it. Our machines, our power, our sky, they all respond, quietly, constantly, to the pulse of our star. Feel the silence here, far beyond Earth, far beyond even Mars and Jupiter. It's wide and dark, but not empty. It never truly is. All around us, space hums with activity, gentle flows of particles, wandering magnetic fields, soft bursts of radiation. Even here, the sun reaches us. Its light takes more than an hour to get this far, but it still arrives, and with it comes the weather. Let's drift slowly past Saturn. Look at those rings, billions of icy fragments, some the size of pebbles, others as big as houses, all spinning in a thin, flat plane around the gas giant. But did you know, even these are shaped by space weather? Solar particles, tiny though they are, chip away at the ice. They can alter the chemistry of the ring material, turning some of the surfaces darker, rougher. And when Saturn's magnetic field catches a sudden solar storm, it crackles with auroras too, just like Earth, only faster, stranger, brighter. Sometimes the auroras here even pulse, a heartbeat of light racing through the upper atmosphere of this giant planet. And it's all because of distant solar storms, flung across hundreds of millions of miles. Now drift lower with me, near the top of Saturn's cloud bands. Feel the massive, invisible strength of the planet's own magnetism. It's so strong that it traps particles, forming radiation belts far more intense than Earth's. But these belts aren't always steady. They change, swell, contract, depending on what the sun sends. The particles ride invisible spirals through the magnetic field, crashing into the upper layers of gas, lighting them up from within. And while you can't hear it, if we could tune our ears to radio waves, we'd hear the eerie songs of Saturn's storm space weather turned into sound. Let's pull away now, rising above the rings, watching as the planet shrinks behind us. The further out we go, the thinner the solar wind becomes, like stretching taffy across billions of miles. But even out here, in the dark, space weather has presence. As we pass Uranus, then Neptune, even Pluto, yes, tiny, icy Pluto, we find that each world has its own dance with the sun. Some have weak atmospheres that puff and shrink depending on solar output. Others have magnetic fields, or traces of them, that respond to solar storms in subtle ways. On Neptune, the auroras flicker in deep blue skies, far fainter than those at Earth. But they're there, faint signs of the sun's distant breath, brushing even the edge of our solar system. Now let's turn our gaze beyond, past the planets, past the edge of the solar wind's reach. Here, the sun's power fades. The solar wind slows, collides with the interstellar medium, that quiet, vast sea of particles that drifts between stars. This is the heliopause, a soft boundary. Not a wall, not a fence, but a gentle transition. And here, space weather becomes something even more mysterious. No longer just about the sun, but about other stars. Cosmic rays, high-energy particles from across the galaxy, zip through this region. They're older than our sun's current storm cycle. They've been traveling for millions of years. And when they arrive near Earth, the solar wind helps shield us from most of them. But when solar activity is low, more of these galactic wanderers make it through. So in a strange way, our sun protects us not only from its own wild weather, but from that of distant stars. Picture yourself floating here, just beyond the bubble of the solar system. You might think it's quiet, and it is, in a sense. But the wind still whispers, just a different wind now. Not solar, but galactic, and space weather, in this deep place, becomes a blend. The quiet pressure of interstellar particles, the occasional nudge of a long-distance flare from a far-off supernova, the ever-present hum of background radiation. Let's turn inward again. We've been to the edge. Let's fly back, slow and smooth, retracing the solar wind as it moves toward the inner planets. See how it flows along the curves of the magnetic field, how it bends and sways. Space weather isn't random. It moves in spirals, loops, bursts. It has rhythm, sometimes fast, sometimes slow, sometimes fierce, sometimes soft, and it always connects back to the sun. Now let's return to the sun's surface. It's time to look closer. See the granules, vast, bubbling cells of hot gas, each the size of a country. They rise, cool, and sink again, over and over. These motions feed the sun's magnetic field, twist it, stretch it, fold it, and every so often that field snaps. That's when a flare erupts, a flash of brightness, like a spark from a campfire, except millions of times more powerful. That spark launches particles, disturbs the solar wind, and sends space weather surging through the solar system. And then there are the coronal holes, dark regions on the sun's surface where the magnetic field opens out into space. From these regions, the solar wind flows faster, straighter, more direct. When Earth crosses the path of one of these streams, our magnetic field wobbles. You might not notice it directly, but your GPS might, or the spacecraft above us. And if the wind carries extra pressure, even the atmosphere swells slightly. Satellites feel more drag. They slow, just a little. That's space weather, invisible and constant, gently pulling on our technology. Reach out with me. Feel the sun's breath on your skin. Not heat, not light, but a faint electric tingle of energy flowing past. That's what our spacecraft feel, what our magnetosphere blocks, what our satellites endure, and what sometimes colors the skies with auroras that make you stop and look up in wonder. Let's move toward Earth again, back to where it all connects. We're drifting high above the North Pole now, watching the auroral oval shift and shimmer. It's like a ring of firelight dancing endlessly in the night sky. Below, scientists track these changes, hour by hour. They know that when space weather grows stronger, the lights grow brighter, but so do the risks. Power grids must be checked. Communications may flicker. Planes flying over the poles may need to reroute. And astronauts aboard the International Space Station, they sometimes move into shielded areas, letting the strongest bursts pass by. They, more than anyone, live inside the story of space weather every day. But don't worry, most of the time our shield holds. Our planet's magnetic field is strong, shaped like a teardrop, compressed on the side facing the sun, stretched into a long tail behind. That tail is full of movement, waves, reconnection, bursts of plasma that flow like underwater currents. This magnetotail is where many geomagnetic storms are born. Energy builds up, then snaps, sending particles hurtling back toward Earth where they light up the sky or ripple through systems below. And even beyond storms and flares, the solar wind keeps blowing. Even on the quietest days, it's always there, always shaping, always touching. This is where we'll pause not to stop, but to take a breath. We've seen space weather from the inside out and the outside in. We've watched it sculpt moons, dance with planets, ripple through rings, and whisper from the edge of the stars. And still, we've barely scratched the surface. If you're ready, we'll continue deeper into the patterns of solar cycles, the way we study space weather, and how it might shape the future of space travel and life beyond Earth. Picture us now gently orbiting Earth from far above. Beneath us, clouds swirl, oceans gleam, and the continents bask in golden daylight or stretch quietly into the night. But above all that, above the blue and the clouds, space weather is always humming. It doesn't stop when the sun sets. It doesn't pause for day or night. The solar wind continues, always streaming outward, always brushing against Earth's invisible shield. And right here, floating beside satellites and space stations, you and I can sense that rhythm, the way the wind strengthens when a solar flare erupts, or settles into a quieter flow when the sun is calm. Now let's lean into the patterns, these solar rhythms that breathe through the universe. The sun isn't always the same. Every 11 years or so, it goes through a full cycle. Sometimes, it's quiet, with just a few sunspots here and there, small dark patches that mark magnetic turbulence. But then, over months and years, activity builds. The sun's surface begins to churn with more intensity. More sunspots appear, more flares leap into space. And the solar wind becomes more unpredictable, more fierce. This is the solar maximum. Imagine the sun, like a slowly waking giant, stretching and shaking off energy in all directions. Flares flare more often. Coronal mass ejections, great arcs of plasma, leap into the solar system like waves from a stormy sea. These are some of the strongest forces in space weather. They can race toward Earth in just a couple of days, carrying billions of tons of charged particles. And when they arrive, they can shake the very edges of our planet's magnetic field. Reach out and feel the tremble in the air here, far above the surface. It's like the quiet thrum of distant thunder. You might not hear it, but Earth's magnetic shield does. It flexes, it bends. And sometimes, it cracks just a little. That's when a geomagnetic storm unfolds. These storms aren't storms in the way we know them on Earth. There's no wind you can feel on your cheek, no rain to splash in. But they're storms nonetheless, vast movements of energy and particles, shifting invisible forces around our planet. They can induce currents in long power lines, confuse GPS signals, and make high-frequency radio chatter fall silent. And yet, they also bring beauty. Look down with me toward the poles. During a geomagnetic storm, the auroras bloom. Not just thin bands, but wide rivers of light, curling and folding across the sky. Greens, purples, deep reds. Sometimes, they ripple like curtains in a breeze. Other times, they pulse like heartbeats. They dance not just above the Arctic and Antarctic, but sometimes much farther south or north, visible in places that rarely see them. This is Earth's way of lighting a lantern against the storm, painting color across the sky. Now let's visit the other side of the cycle, solar minimum. In these years, the sun rests. Fewer sunspots, fewer flares. The solar wind softens, the storms quiet. But even this quiet has its mysteries. During solar minimum, more cosmic rays from the galaxy make their way into the solar system. Without the strong solar wind to block them, they drift in greater numbers toward Earth. These particles are older than we can imagine, many born in supernovae long ago, from stars that lived and died before our own solar system even formed. Imagine catching one of these ancient particles in your hand. It would pass through silently, too small to see, too quick to stop. But it tells a story of exploding stars, of galactic journeys, of the vastness that surrounds us. And during solar minimum, those stories arrive more often, drifting quietly through our skies. Let's shift again, feel that gentle tug? We're heading back to our moon now. It's so close to us, yet so different. Without a magnetic field, the moon doesn't have a shield like Earth. Space weather touches it directly. During strong solar storms, the surface is bombarded. Fine dust gets charged and might even lift from the ground in tiny arcs. Over time, this bombardment slowly alters the surface, a process called space weathering. It makes the lunar soil darker, rougher, and coats the grains with tiny bits of glass formed from countless microblasts. And this tells us something important. When we send astronauts back to the moon, or rovers to Mars, or probes deep into the outer solar system space, weather matters. It isn't just something beautiful or curious. It's something we need to understand, to plan for, to live with. Let's glide gently now toward Mars. See its rusty surface, carved by old rivers, dotted with craters. Unlike Earth, Mars once had a magnetic field, but lost it billions of years ago. Without that shield, its atmosphere was slowly stripped away by the solar wind. You can almost feel it, the wind brushing against the thin Martian air, carrying it off molecule by molecule, not in days or years, but over millions of years. That's the power of space weather, patient, silent, relentless. And still, Mars holds on to secrets. In places, it still shows auroras not from a global magnetic field, but from pockets of ancient magnetism frozen in its crust. These small regions still dance when solar storms pass by. Not with the grandeur of Earth's polar lights, but with quiet, flickering hints like candlelight behind stained glass. As we hover above Mars, you might notice the faint trace of dust storms below. Space weather plays a role here too. High-energy particles from solar flares can affect the planet's upper atmosphere, altering temperatures, nudging winds. Everything in space is connected. Now look past Mars, toward the asteroid belt. It's not the thick field of rubble you might expect. Space is still mostly empty here. But the solar wind reaches this far, whispering across the surface of rocks that haven't changed much in billions of years. Some of these asteroids are metal, some are stone. All of them are weathered not by rain or frost, but by solar radiation and tiny impacts. In fact, the color of an asteroid can change over time, as it's exposed to more and more solar wind. And when one of these space rocks is knocked into a new orbit, perhaps toward Earth, scientists study its surface to guess how long it's been wandering and how space weather has changed it. Let's move deeper again, toward Jupiter. Feel the sudden swell of energy as we near the biggest planet in our solar system. Jupiter is wrapped in a magnetic field so huge, it could stretch across our entire sky from horizon to horizon. It spins fast every 10 hours, and its magnetic field whips around with it. This field traps particles from the solar wind and from its volcanic moon, Io. The result? A radiation environment so intense that spacecraft must shield themselves just to survive a brief pass. But again, space weather is part of the story. Jupiter's magnetic field changes with the solar cycle. During solar maximum, it becomes more turbulent. Auroras flash and flare around its poles, far brighter than Earth's, and storms ripple across its magnetosphere like thunder on an alien world. Stay with me here. Floating above those clouds, the giant storm we call the Great Red Spot churns below. Above it, invisible waves of magnetic energy ripple through the upper layers of Jupiter's atmosphere. And now and then, a burst from the sun reaches out, stirs those waves, adds just a little more motion to the mix. All of it connected. Everywhere we go in the solar system, space weather is there not just as a background detail, but as a living force. It shapes what we see. It molds what we don't. It changes planets, sculpts moons, whispers through rings, and tugs at spacecraft. And there's so much more to share, from how scientists watch the sun with satellites and telescopes, to how new missions are being designed to survive stronger storms. And even, far beyond, how space weather might look around other stars entirely. Just beyond Jupiter, let your gaze drift outward. The solar wind doesn't stop at Mars or Jupiter. It pushes farther still, past Saturn, where rings shimmer like delicate halos in the distance. Space weather travels even here, brushing softly across each icy rock in those magnificent bands. Picture the tiny particles of the rings, bits of ice, dust, and rock, all caught in a gravitational dance. Each one is touched by sunlight and solar wind. Slowly, their surfaces are etched and worn. Not quickly, but over centuries, millennia. Saturn's magnetic field, like Jupiter's, is enormous. Though quieter, it too captures charged particles. Auroras form at Saturn's poles, glowing with ghostly light that dances across clouds of methane and ammonia. Sometimes the auroras here shift in response to solar storms that began days earlier on the Sun. Imagine seeing that shift from the far side of the rings, a faint ripple of green and blue lighting the planet's curve. It feels alive, doesn't it? Like even from this distance, the Sun whispers to the edge of the solar system, and the planets answer back. Let's drift outward more, calmly, slowly. Beyond Saturn, space becomes colder, darker, and even quieter, but the solar wind still flows. It's thinner here, more diffuse. Yet still, it moves. Out past Uranus and Neptune, it begins to slow. These giants have their own weather. Of course, massive storms, supersonic winds. But even here, solar activity plays a role. It touches their magnetospheres, stirs their atmospheres. Sometimes it sparks faint auroras at their distant poles. Neptune's auroras are hard to see, but they're there. Not like the brilliant shows on Earth or Jupiter, but quiet flickers deep in the blue. Think about that for a moment, a planet nearly 3 billion miles away, still feeling the breath of our star, still answering with its own light. Farther still, beyond the planets, we reach the edges of the solar system. Here, the solar wind slows to a crawl. It starts to press against the interstellar medium, the space between stars, filled with ancient dust and the faint remains of long-dead suns. This borderland is called the heliopause, and it's where the influence of our sun finally begins to fade. Imagine standing there with me. Behind us, the sun is still visible, a bright point surrounded by the scattered planets. Ahead of us, the galaxy stretches endlessly, full of stars and mysteries. Even here, space weather from our sun meets and merges with energy from beyond, a quiet boundary, a cosmic handshake. Voyager 1 crossed this region years ago. It's still sending back messages, faint signals that take over 20 hours to reach Earth. From where Voyager is now, space weather looks different. No longer shaped only by the sun, but by the entire galaxy. And yet, even this far away, the echo of solar flares, the pattern of the solar cycle, still leave a mark. Let's head back now, slowly retracing our path. We pass Neptune again, then Uranus, drifting by the thin rings, the icy moons. Saturn comes back into view, its rings glowing softly. Then Jupiter, swirling and majestic. And eventually, Earth appears once more, blue and bright, with auroras shimmering like curtains in the sky. Hover here with me, just above Earth. Watch the northern and southern lights twist and glow. Think of all the invisible activity that led to these colors: particles from the sun, electric currents in Earth's magnetosphere, atoms in the atmosphere catching energy and releasing it as light. A cosmic ballet, quiet but constant. This is space weather, not a storm you can feel on your skin, but a force that shapes the universe. It touches everything, connects everything. From the sun to the edge of the solar system, it flows. And now, let your thoughts drift not just across space, but back in time. Let's look at the sun in its earliest days, just waking up as a newborn star. Billions of years ago, before planets had fully formed, the sun was already spinning, glowing, and sending out waves of energy. Its winds were stronger then, more chaotic. The early solar system was a wild place, full of storms and swirling clouds. You might notice how the young planets were shaped by this activity. Mercury, closest to the sun, was scorched and battered. It lost much of its atmosphere, stripped away by the constant bombardment of solar particles. Venus developed a thick, swirling cloak of gas, trapping heat inside like a furnace. And Earth, somehow, found balance. Our magnetic field rose like a shield, deflecting the most dangerous blasts while allowing just enough warmth and light to nourish life. Reach out and feel that balance now, right here in Earth's orbit. The sun still sends us its power, solar storms still surge, but Earth dances with it, swaying, shifting, surviving. The atmosphere glows gently, the poles shimmer. Even when storms disrupt our satellites, knock out radio waves, or ripple through the power grid, we adapt, we listen, we learn. Drift now toward Mars. This dry, dusty world once had rivers, maybe even oceans, but its magnetic field faded long ago, and with it, much of its atmosphere was lost. The solar wind, always brushing by, slowly peeled it away. Today, we see the echoes of that change in the gullies and canyons. Space weather, acting over eons, helped reshape an entire planet. And think about this: if we ever live on Mars, we'll need to understand that space weather more than ever. We'll need shelters, shielding, and careful timing. Solar flares. There aren't just beautiful lights. They could be dangerous flashes, invisible but powerful. So, even as we dream of stepping on red soil, we carry with us a respect for the sun. Back near Earth, satellites orbit high above, quietly monitoring the sun's activity. They watch for flares, count the sunspots, measure the wind. This constant awareness helps us prepare. It helps pilots, astronauts, engineers. It helps keep lights on and signals strong. And when a particularly strong solar flare erupts, these satellites send warnings. Power stations brace. Airlines adjust routes. Even astronauts in space stations take shelter in shielded areas. All of this because of invisible waves that travel millions of miles from the sun to us. Let's imagine now that we're floating beside one of those satellites. It hums quietly, covered in solar panels, spinning slowly. It watches the sun every day, patiently. A burst of light appears, a flare. The instruments detect it. Instantly, a message races back to Earth. In that moment, we witness the speed of light, the power of awareness. Then, hours or days later, the slower particles arrive. A coronal mass ejection, or CME, pushes through space. These waves can be immense, like a tide moving through the solar system. When they reach Earth, they shake our magnetic field, stir up the sky. That's when the auroras come alive. That's when satellites might flicker. And yet, with each storm, we grow more prepared. Feel the wonder of it with me. Every second, the sun breathes energy into the solar system. Not always gently, but always beautifully, and always with patterns we can learn to read. Let's float a little higher now, where Earth's shadow begins to blur into the blackness beyond. Look down with me. See that delicate curve along the planet's edge? That's the atmosphere, thin, fragile, glowing faintly. It protects every breath we take, every signal we send, and every journey we begin out into space. And just above it, space weather flows invisibly, brushing past our satellites, tugging gently at Earth's magnetic field. There's a quiet rhythm to it all. The sun spins, its surface shifting and swirling like a pot of golden fire. Every few minutes, a small flare bursts from its surface. Most of them are harmless, just little sighs of heat and light. But once in a while, something much bigger happens. A great twist in the magnetic fields snaps and hurls charged particles across space. When these reach Earth, they ripple through our magnetosphere like pebbles tossed into a pond. You can almost hear it, can't you? That silent tremor through the invisible shield. Instruments pick it up: tiny shifts in magnetic strength, small changes in radiation levels, and far below, deep in the Earth's crust, those signals can even stir electric currents in the ground. Yes, space weather reaches that far. It touches stone. It moves wire. Now picture yourself drifting near a power grid, somewhere in the far north. Long wires stretch across snow-covered fields. These lines aren't just carrying electricity, they're listening to space. When a solar storm hits, the magnetic fields around those wires shift ever so slightly, and in doing so, they generate currents, not from any power plant, but from the sky. It's beautiful, but it can be dangerous. Too much current, and systems can overload. Transformers hum a little louder. Circuit breakers blink. Lights may flicker in cities hundreds of miles away. But don't worry, we've learned to listen. Engineers design defenses. Systems now react faster. Some parts of the grid even go into protective sleep, just for a moment, to ride out the storm. It's all part of how space weather shapes our modern lives silently, invisibly, yet undeniably. Now let's turn to the skies again. Not the stars this time, but the plains. At high altitudes, near the poles, the air is thinner, and that means solar particles can sneak closer to the surface. Imagine flying in a jet, cruising over the Arctic. The windows rattle gently. The engines hum. But outside, far beyond the fuselage, space weather is at work. High-energy particles from a solar flare stream downward, bouncing against the magnetic field. Most are deflected, but some slip through. That's why, during strong solar storms, flights are rerouted away from the poles, not because of turbulence, but because the radiation levels can spike. Pilots and passengers alike are safer when they steer into calmer skies, and radio communications, especially over oceans, can become patchy, not from clouds, but from the shifting dance of solar particles in the upper atmosphere. It's incredible, isn't it? A storm that began on the sun, nearly 100 million miles away, changing the path of a single plane, changing how voices are heard between continents. Let's dip lower now, into the atmosphere itself. Around 60 miles up, in a place called the ionosphere, space weather truly comes alive. This is where solar energy meets Earth's air and turns it into a glowing, buzzing sea of charged particles. It's not something we see with our eyes most days, but our technology feels it. GPS signals pass through here. Radio waves bounce and bend in this layer, and when the sun gets especially active, the ionosphere stirs and swells like a restless ocean. That's when GPS signals might wander just a little, a few meters off. Not a big deal for someone using it to find a coffee shop, but for ships at sea or planes coming into land, even tiny shifts matter. And so, again, we watch. Satellites measure the shape of this layer. They map its motion, predict its moods. It's like tracking a weather system, but in the sky above the sky. And did you know during some solar events, radio stations can suddenly go silent? A whole band of frequencies might vanish for minutes or hours, swallowed by a wave of solar particles. Pilots, mariners, even search and rescue teams rely on those frequencies. That's why space weather forecasting has become not just a curiosity, but a necessity. Let's glide now toward the International Space Station. It circles Earth every 90 minutes, a brilliant point of light against the dark. Inside, astronauts float gently, busy with science and observation. But when the sun erupts, they know it. They get alerts. They move to shielded areas. Sometimes, experiments are paused. Not because of a machine failure, but because of a wave of invisible particles now washing over the station. They can't see the particles, but instruments detect them. Radiation levels rise. And yet, calmly, without panic, they wait. Space weather is something they live with every day. It's a reminder that even here, even in this quiet outpost, the sun is always in touch. Now think of the future. Missions to the moon, to Mars, to asteroids and beyond. These journeys will pass through regions where space weather is harsher and protection is thinner. Engineers are already designing better shielding, faster alerts, smarter spacecraft that can turn or hide from the worst of solar storms. And scientists are learning to read the early signs, the flicker of a new sunspot, the twist of magnetic loops, the pattern of solar cycles. Because if we're to live and work in space, we need to know not just where we're going, but what space is feeling that day. Let your imagination float farther now to a spacecraft orbiting another star, one of the exoplanets, hundreds of light years away. There too, the host star shines and breathes. There too, space weather shapes the skies, stirs the atmosphere, perhaps even sculpts the surface. Could alien civilizations be watching their own auroras? Could they have their own satellites, their own alerts, their own names for the flares that shape their worlds? We don't know yet, but what we do know is this: space weather is universal. Every star whispers to its planets. Every planet answers in light, in movement, in magnetism. And we, on our small blue world, are part of that endless conversation. Look back with me now, not just in space, but in time. Before satellites, before telescopes, before electricity, humans were already watching the sky. Picture a group of people thousands of years ago standing under the night. No cities, no lights, just stars above and the hush of wind in the trees. Suddenly the sky flickers green. Curtains of light ripple across the horizon. The first auroras. They didn't call it space weather then, but they saw its beauty, its mystery. Some thought it was a sign from the gods, others, a warning. In ancient China, careful records were kept red vapors in the sky, glowing spears of light. The same in Norse cultures, where shimmering skies were said to be reflections from armor in distant battles. And in North America, the Inuit believed the lights were spirits, playing in the heavens. None of these people knew about the sun's charged particles or the magnetosphere, but they were watching the same dance we see today, a cosmic story told in color and light. Now fast forward to the 1800s. The sky flares again, but this time it's different. In 1859, the strongest solar storm ever recorded erupted from the sun. It would later be called the Carrington event, named after the astronomer Richard Carrington, who saw a sudden, blinding flash on the sun through his telescope, a solar flare. Just a day later, Earth felt the impact. Telegraph systems sparked and failed. Wires caught fire. Operators received shocks through their equipment. And across the globe, auroras flared so brightly they were seen near the equator. In Colorado, miners thought morning had arrived hours early. In the Caribbean, the night sky pulsed red and green. No one understood what had happened. Not fully, but it marked a turning point. This was the beginning of our understanding, the realization that the sun was not just a light in the sky, but a dynamic, active force. A star capable of reaching across space and touching the very systems we built on Earth. Today, we remember that storm not with fear, but with curiosity, because now we have the tools to understand it. Let's step inside one of those tools. Imagine yourself aboard a space observatory, a spacecraft called the Solar Dynamics Observatory, or SDO. It's orbiting high above Earth, always turned toward the sun. Every 10 seconds, it snaps an image, not in visible light but in ultraviolet, X-ray, and extreme wavelengths that reveal the sun's hidden layers. Through SDO's eyes, the sun doesn't look smooth and calm. It's alive, roiling, bubbling with plasma. Loops of fire arc into the air, hundreds of times taller than Earth. Dark spots crawl across the surface, sunspots, cooler regions twisted with magnetic energy. Sometimes, those spots snap, a flare bursts outward, and SDO records it all. Now zoom in even closer, peer into those magnetic loops. See the motion, not just fire, but order. The sun is magnetic. Every part of it is wrapped in fields and currents. These fields change over time, flipping polarity about every 11 years. That's the solar cycle. During solar maximum, the sun is restless. More flares, more sunspots, more chance of storms reaching Earth. And during solar minimum, it's quieter. The cycle ebbs and flows, like a heartbeat in deep time. This cycle has been going on for billions of years, and we've only just begun to understand it, but we've learned enough to predict, to prepare. Let's visit the scientists now here on Earth. A solar physicist watches real-time data on a glowing screen. a new flare appears on the far side of the sun. The model updates. If that flare becomes a CME, it could reach Earth in 36 hours. The forecast is sent out to governments, to space agencies, to industries that depend on timing and technology. And somewhere, a satellite operator repositions their craft. A power grid runs diagnostics. An airline adjusts its flight plan. 1,000 small actions ripple outward, all from one burst of light on the sun. This is how we live with space weather now, not in fear, but in partnership. We read the signs, we watch the patterns, we listen. And now imagine the future, not just months or years, but centuries ahead. Picture a colony on the moon, grey soil beneath silver domes. People walking in sealed suits, tending machines, growing food in sunlight filtered through protective glass. Even here, space weather matters. Solar storms could be dangerous. So high above, orbiting satellites form a net, constantly watching, constantly measuring. Alerts are swift. People move inside. Systems adjust. Then, when the storm has passed, life continues. Farther still, Mars. A small city, red dust swirling outside transparent walls. This world has little magnetic protection, but humans have built new defenses, underground shelters, radiation shields, smart structures that detect and deflect. Solar flares that once stripped the Martian air now meet prepared minds and steady hands. And one day, perhaps, ships will travel between stars, crewed missions to other suns. There, the rules of space weather might be different. Alien stars might flare brighter, or twist in ways our sun never has. But we'll be ready, because we've learned from our star. We've grown with it. We've listened to its quiet language. And that language speaks of movement, of connection, of energy flowing from one body to another, endlessly. So here we are now back near Earth, just above the auroras. The sky flickers and flows with green, violet, and red. Below, the world sleeps, mostly unaware. But above, space weather whispers on. The sun is speaking, and we are finally learning to listen. Now, let me take you on a journey not just across space, but through time to where space weather has left its fingerprints on Earth itself. Imagine ancient forests, their tall trees standing silently for centuries. And deep inside those tree rings, hidden like secret diaries, lie clues about the sun's moods, long before humans had satellites or telescopes. Scientists studying these rings have found sudden spikes in radioactive carbon bursts caused by powerful solar storms, sending floods of energetic particles into Earth's atmosphere. These particles collide with nitrogen atoms, producing carbon-14, a radioactive isotope that trees absorb as they grow. So every ring, every layer of wood, holds a whisper of solar fury from thousands of years ago. Like messages in a bottle, these clues help us understand how often the sun throws tantrums, how fierce they can be, and how Earth's magnetic shield responds. And it's not just trees. Ice cores from Greenland and Antarctica carry similar stories. Trapped in frozen layers, isotopes created by cosmic rays show us patterns of space weather reaching Earth through the ages. They reveal times when our planet was bombarded by cosmic storms, some far stronger than anything we've seen in recorded history. This natural archive tells us one thing loud and clear: space weather is ancient. It has shaped Earth's environment for eons, and it continues to shape our world today. Now, turn your eyes upward again, not to the Earth beneath your feet, but to the comets streaking through the solar system. Comets, those icy travelers, are like delicate cosmic flags waving in the solar wind. As they near the sun, the heat vaporizes their frozen surfaces, creating spectacular tails that stream millions of miles behind them. But the direction and shape of those tails, they are sculpted by space weather. The solar wind, a steady flow of charged particles from the sun, pushes comet tails away from the sun, no matter which way the comet itself is traveling. It's a beautiful reminder that space weather doesn't just touch planets. It reaches out, shaping the cosmos in subtle but visible ways. Imagine watching a comet's tail shimmer and sway, its graceful curve a silent dance choreographed by solar winds and magnetic fields. And yet, despite all its power, space weather also brings moments of breathtaking beauty. The auroras, those shimmering curtains of light, are the most vivid signs. When charged particles funnel into Earth's polar skies, they collide with atoms in the atmosphere, exciting them until they glow in vibrant greens, reds, and purples. It's a light show like no other, a cosmic symphony played out in the sky. And for those lucky enough to witness it, the aurora is a reminder that space weather is not just a force to be reckoned with, it's a bridge between the heavens and our lives on Earth. As we continue to explore this story, remember, space weather is a vast, invisible web connecting star and planet, machine and human, past and future. It shapes our technology, our culture, our dreams, and the more we learn to read its signals, the better we prepare for tomorrow's storms, and the more deeply we appreciate the sun's eternal dance. Now, let's shift our focus from the grand cosmic scale down to the intricate technology that humanity has woven into the fabric of space weather monitoring. Imagine the silent sentinels orbiting Earth, a fleet of sophisticated satellites, each designed for a specific mission in the dance with our star. Take the Discover spacecraft, positioned 1 million miles away at the Lagrange point between Earth and the Sun. It acts like a solar weather station, constantly measuring the solar wind before it even reaches Earth. Discover's instruments detect the speed, density, and magnetic direction of charged particles racing towards us. Its early warnings are crucial. They give power grid operators, satellite controllers, and mission planners precious minutes to prepare for incoming storms. Consider too the ACE spacecraft, working alongside Discover, creating a layered defense through real-time data. Together, these satellites create a mesh of observations that turn invisible solar tempests into readable information. Now, think about the complexity of space weather's effect on modern technology. The same particles that create stunning auroras can wreak havoc on GPS systems, disrupting navigation for planes, ships, and even smartphones. High-frequency radio communications vital for aircraft and emergency responders can be blacked out by ionospheric disturbances triggered by solar activity. Even satellites, our eyes and ears in space, are vulnerable. Energetic particles can penetrate shielding, causing temporary malfunctions or, in worst cases, permanent damage to sensitive electronics. This phenomenon, known as single event upsets, means a stray particle can flip a bit in a computer's memory, leading to glitches or data corruption. Engineers combat these risks through clever design, hardened electronics, redundant systems, and shielding, but the threat is ever present. That's why understanding space weather isn't just academic, it's vital to keeping our global infrastructure running smoothly. Look closer at the effects on aviation. Polar routes, often the shortest paths between continents, take planes over regions where Earth's magnetic field is weaker, and space weather can be more intense. During strong solar storms, increased radiation exposure is a concern for crews and passengers, and communication blackouts force rerouting to safer paths. Airlines must coordinate with space weather centers daily, balancing safety and efficiency in real time. Beyond Earth's immediate environment, let's consider astronauts living aboard the International Space Station, ISS. Floating hundreds of miles above us, they are exposed to heightened radiation levels compared to people on the surface. Space agencies monitor solar activity carefully, alerting crews when a solar storm approaches. In these times, astronauts take shelter in specially shielded areas of the station, reducing their exposure to dangerous particle flux. But as humanity eyes journeys to the Moon, Mars, and beyond, space weather presents even greater challenges. Long-duration missions outside Earth's protective magnetosphere mean astronauts will face prolonged radiation exposure. Shielding becomes more complex, involving advanced materials and possibly magnetic or electric fields to deflect charged particles. Now imagine the design of spacecraft, with active space weather defenses, sensors detecting incoming storms, systems that can adjust orientation or power down sensitive equipment, and habitats engineered to minimize radiation risks. These innovations represent a new frontier, a blend of engineering, physics, and space weather science that will safeguard humanity's future among the stars. On a different note, think about the profound impact space weather has on Earth's climate systems, a topic still unfolding in research. While the sun's overall energy output varies slightly over the solar cycle, subtle changes in ultraviolet radiation influence the upper atmosphere's chemistry and circulation patterns. These effects cascade downward, potentially modulating weather and climate phenomena on Earth. Some studies suggest solar activity might play a role in phenomena like the North Atlantic Oscillation or the El Niño Southern Oscillation, though these relationships are complex and intertwined with many other factors. Understanding these connections is critical as we seek to disentangle natural variability from human-induced climate change. Finally, let's touch on one of the most fascinating intersections: space weather and space debris. The near-Earth environment is increasingly crowded with defunct satellites, spent rocket stages, and fragments from collisions. Solar activity influences this environment by expanding Earth's upper atmosphere during active periods, increasing drag on low Earth orbit debris and satellites, sometimes altering their orbits. This natural atmospheric cleaning helps reduce debris over time, but it also adds unpredictability to spacecraft operations and collision risk assessments. Managing space weather is therefore a vital piece of the puzzle in ensuring the sustainability of Earth's orbital environment. Picture yourself stepping into the control room of a space weather center. The atmosphere buzzes quietly with focused energy. Banks of screens glow softly, each displaying a different view of the Sun or Earth's magnetic shield. You feel the hum of machines, the soft click of keyboards, and the calm, steady voices of experts sharing updates. Here, the guardians of our cosmic environment keep vigil. Their work is like listening to a distant heartbeat, a subtle rhythm that guides humanity's response to invisible storms millions of miles away. Imagine the moment a sudden solar flare bursts into life on the Sun's surface. It's like a giant cosmic hiccup, a brilliant flash of light erupting in brilliant shades of white and yellow, hotter than millions of kitchen ovens combined. Within minutes, satellites detect an energetic wave rushing toward Earth. In the control room, alarms softly beep. Analysts track the flare's path, its speed and intensity. Each passing second stretches longer in their minds as they calculate impact times. Communications with airlines, power companies, and astronauts switch from routine chatter to urgent coordination. Feel the tension, but also the confidence born of preparation and knowledge. This is no unexpected chaos. This is a challenge met by decades of study and technology, a dance choreographed with precision. Outside, the sky may still look calm and blue, but invisible rivers of charged particles flow swiftly through space, interacting with Earth's magnetic field. Picture these magnetic lines bending and twisting like ribbons caught in a gusty wind. When these lines reconnect or snap, energy is released, sending surges of particles toward the poles. This magnetic ballet creates the aurora's ethereal curtains of green, red, and violet light. They ripple and shimmer, as if nature's own light show is being played for those watching silently beneath. Reach out and imagine the faint cold air on your skin as you stand beneath these lights. Hear the silence that feels full, as if the sky itself is holding its breath. But there's more to space weather than the beautiful auroras. Let's shift to a more hidden and potentially dangerous realm: radiation storms. During intense solar events, charged particles, mainly protons, can surge outward in massive bursts. These high-energy particles slam into spacecraft, threatening onboard electronics and, more seriously, any humans traveling beyond Earth's protective shield. Visualize astronauts orbiting in the ISS. The station's metal hull offers some protection, but during a solar proton event, radiation levels spike. Crews move quickly to designated safe zones, thicker walled compartments designed as shelters. Imagine their thoughts a mixture of awe at witnessing the sun's power up close, and a sober awareness of the invisible dangers it poses. Even here, space weather reminds us that the sun is a living star, dynamic and sometimes unpredictable. Back on Earth, space weather's fingerprints are found in more subtle ways. Consider power grids stretching across continents, humming quietly as they supply our homes. Powerful solar storms induce electrical currents in these vast networks, sometimes overloading transformers or causing temporary blackouts. Recall the Great Quebec Blackout in 1989, when a geomagnetic storm caused by a solar flare knocked out power for millions. It's a reminder that space weather isn't just cosmic spectacle, it touches our daily lives in very real ways. Now, picture yourself as a pilot soaring high above the poles. You're in a cockpit filled with instruments, flying along routes where communication can be spotty. During solar storms, radio signals fade, GPS signals waver, and the cosmic radiation dose climbs. Pilots reroute flights, avoid polar paths temporarily, all while relying on space weather forecasts crafted from those distant satellites you imagined earlier. And here's a fascinating twist. Space weather affects even the tiniest bits of matter, like the dust and particles orbiting Earth. During intense storms, the atmosphere can swell, increasing drag on satellites and space debris, subtly changing their orbits. It's like invisible hands gently pushing and pulling objects in space, reminding us how connected everything truly is. Imagine the challenges this creates for scientists tracking thousands of pieces of space junk, working tirelessly to prevent collisions and keep the space around Earth safe for satellites and astronauts. As we drift through these stories, it becomes clear that space weather is a cosmic conversation between the sun and planets, between technology and nature, between human curiosity and the vast unknown. So as you settle in beside me now, imagine we're both gazing up at the night sky. Stars twinkle softly, and somewhere beyond them, the sun is stirring, sending out another ripple of particles and light. Feel the hum of the universe all around us, quiet but alive. This is space weather, a force unseen but felt, a story ever unfolding in the skies above. Now, let's travel back in time, not too far, but to the days before our modern instruments, when people first began to notice the strange lights dancing in the night sky. Imagine a chilly winter night in ancient times, under a vast dome of stars. Early observers, without telescopes or satellites, would have seen the auroras flickering far north. To them, these shimmering curtains of green and red were mysterious and powerful signs. Many cultures wove stories around these lights. Some believed they were the spirits of ancestors. Others saw them as omens or messages from the gods. In Scandinavia, the Vikings called the auroras the fire of the Valkyries, fierce warrior maidens riding across the sky. Indigenous peoples of North America told of celestial dances, fires burning on the horizon, or the glow from great spirits playing in the heavens. These myths, full of wonder and respect, show how space weather has always touched human imagination, long before science could explain it. Fast forward to the 19th century, when scientists began to connect these lights to the sun's activity and Earth's magnetic field. It was a breakthrough moment. The auroras were no longer magic, but a natural phenomenon linked to invisible forces shaping our planet's environment. This connection opened a new chapter. It spurred the invention of instruments to measure magnetism, the launch of the first weather balloons, and eventually, the space age with its fleet of satellites. Each step forward gave us a clearer picture of the sun's restless nature, and with it, a better understanding of how to live with space weather's whims. Now, looking ahead, imagine the future of space weather science. Picture vast networks of satellites not just around Earth but throughout the solar system, forming a cosmic weather map. These satellites will relay information in real time, helping spacecraft navigate safely through solar storms, guiding astronauts on journeys to Mars, or even out to the moons of Jupiter and Saturn. Advanced AI systems will analyze this flood of data instantly, predicting storms days or weeks before they hit. This could give humanity a new kind of foresight, a way to prepare for the sun's moods as reliably as we do for terrestrial weather. Beyond that, imagine new technologies harnessing space weather itself. Could solar storms be tapped as power sources? Could we design spacecraft that ride solar wind currents, gliding across space with little fuel? Scientists are already dreaming about space sails, enormous, ultra-thin sheets that catch the solar wind, propelling probes across the solar system at unprecedented speeds. These sails would turn solar storms from hazards into highways. Picture yourself gently floating far above the familiar blue surface of Earth. Below you, the oceans shimmer under sunlight, and the continents stretch out like a delicate patchwork quilt. But surrounding it all, like an enormous bubble of unseen force, is Earth's magnetosphere, our planet's magnetic shield. This shield is invisible to the eye, but its presence is as real as the air we breathe. Imagine this magnetosphere as a giant, protective cocoon, crafted by the swirling iron deep within Earth's core. This core is a roiling ocean of molten metal, spinning and churning with such vigor that it creates a powerful magnetic field reaching far out into space. This magnetic force extends tens of thousands of miles beyond the atmosphere, wrapping Earth in a magnetic embrace that deflects much of the solar wind's charged particles. Now, feel the invisible pressure of the solar wind, a constant stream of charged particles flowing outward from the sun at speeds of hundreds of miles per second. This wind, though tenuous and diffuse, carries immense energy. As it rushes toward Earth, it collides with the magnetosphere's outer boundary, compressing it on the side facing the sun and stretching it into a long tail on the opposite side. Imagine this side facing the sun being pressed in like the bow of a ship cutting through waves, while the night side trails behind like a streamer caught in a breeze. This boundary is called the bow-shocker turbulent frontier, where the solar wind slows and diverts, its charged particles deflected by the magnetic field. It's a chaotic region, but one that plays a vital role in protecting Earth from the full brunt of solar storms. As you drift through this invisible shield, picture the constant tug of particles trying to breach the barrier. Most are turned away or caught in trapped paths circling Earth, forming the Van Allen radiation beltstwo donut-shaped rings of high-energy particles, orbiting thousands of miles above the surface. These belts act like cosmic moats, capturing and holding charged particles, preventing many from reaching the atmosphere. But sometimes, during powerful solar events, the magnetosphere's defenses are tested. Imagine a giant wave of particles, hurled from a solar flare or coronal mass ejection, crashing into the magnetosphere with overwhelming force. The magnetic field is stretched, bent, and occasionally broken, allowing bursts of charged particles to surge toward Earth. These particles spiral along magnetic field lines toward the polar regions. Now, picture standing under the northern or southern skies, where these particles enter the atmosphere and collide with oxygen and nitrogen atoms. These collisions excite the atoms, causing them to glow in breathtaking color shades of green, red, purple, and pink. The auroras, our planet's majestic light shows, are born from these invisible cosmic interactions. Reach out and imagine the gentle warmth of these glowing lights on your face as you watch ribbons of color ripple across the night sky. These lights are not only beautiful, they are the visible heartbeat of space weather's dance with Earth. But space weather's influence extends far beyond just the auroras. Let's consider the technology we rely on: everyday satellites circling Earth, GPS signals guiding our way, power grids lighting up our cities, and radio waves connecting voices across continents. All of these systems can be affected by the invisible storms whipping through space. When a powerful solar storm strikes, charged particles can induce electrical currents in power lines, causing surges that may lead to blackouts. Satellite electronics, delicate and sensitive, can be overwhelmed or damaged. Radio communications can fade or drop entirely, especially in high-latitude regions closer to the poles. This is why scientists and engineers work tirelessly to monitor the sun's activity, providing warnings and safeguards. Imagine a control room filled with experts watching screens flicker with real-time data from satellites and ground-based sensors. When a solar storm is detected, alerts are sent worldwide. Power companies prepare to isolate vulnerable transformers. Airlines reroute flights away from polar paths where radiation exposure is higher, and astronauts aboard the International Space Station move to shielded compartments. Think about the profound connection here. We live on a small blue planet, orbiting a single star. Yet our technology and safety depend on understanding invisible forces hundreds of millions of miles away. Now, picture the Carrington event of 1859, the largest recorded solar storm in history. Telegraph systems across Europe and North America failed or sparked fires. Some operators received electric shocks. Auroras were seen as far south as the Caribbean. Imagine witnessing that sky ablaze with strange colors. The night turned bright as day in some places. If such an event occurred today, with our dependency on electronics, the impact would be enormous. That's why modern space weather forecasting is vital, giving humanity a chance to prepare and protect. Looking forward, imagine future missions and technology dedicated to understanding space weather in even greater detail. Satellites positioned between Earth and the Sun, constantly scanning for solar flares and plasma waves. Arrays of ground sensors tracking geomagnetic changes. Models that predict not only when a storm will arrive, but how it will affect every inch of our planet. In the coming decades, as humanity ventures further into space, sending astronauts to Mars, establishing lunar bases, exploring Jupiter's icy moons, understanding and forecasting space weather, will be crucial. Without the protective embrace of Earth's magnetosphere, these explorers will face harsh radiation from solar storms. Designing habitats and spacesuits to shield them, planning missions around solar cycles, will be as important as packing oxygen and food. So, as we hover here in Earth's magnetic embrace, take a moment to feel the constant energy flowing around us. This shield is a testament to the delicate balance that sustains life, technology, and dreams of exploration. Imagine drifting away from Earth, leaving behind the protective cocoon of its magnetosphere. As you move outward, you come upon the moon, our silent, cratered companion. The moon lacks a global magnetic field, and with no atmosphere to shield it, its surface bears the scars of space weather in stark detail. Picture countless tiny impacts from solar particles and cosmic dust, slowly altering the regolith, the dusty soil that blankets its face. Without a magnetic shield or atmosphere, the lunar surface is directly exposed to the solar wind's charged particles. Over billions of years, this relentless bombardment has changed the chemistry of the soil, creating a thin, electrically charged layer called the lunar exosphere. Scientists study this weathering to understand not only the moon's history but how to protect future explorers from harsh radiation. Now, let your gaze wander farther to Mars, the red planet. Once a world with flowing water and perhaps even life-friendly conditions, Mars tells a story deeply shaped by space weather. Unlike Earth, Mars has only patches of magnetic fields, remnants from an ancient global magnetosphere that faded away. Imagine the solar wind sweeping over its surface, peeling away its atmosphere bit by bit, leaving a thin, fragile veil. Visualize the dusty Martian skies as solar storms occasionally stir them, sometimes raising planet-wide dust clouds that cloak the surface in eerie orange twilight. These storms not only shape weather on the ground, but interact with charged particles high above, creating faint auroras near the poles. Think about the robotic explorers we've sent there, instruments braving the harsh environment, relaying data back to Earth. They must withstand not only freezing temperatures and dust, but also bursts of energetic particles from the sun, a constant reminder of Mars's vulnerability. As we continue outward, you arrive near the gas giants Jupiter and Saturn, worlds of swirling storms and powerful magnetic fields far larger and stronger than Earth's. Jupiter's magnetosphere, the largest structure in the solar system, dwarfs even the Sun in size when stretched out. It captures and accelerates charged particles, creating intense radiation belts and stunning auroras at its poles. Imagine standing near Jupiter, surrounded by a fierce, invisible storm of particles whipping through space. These charged particles come not only from the Sun but also from volcanic eruptions on Io, one of Jupiter's many moons. Io's sulfurous plumes feed material into Jupiter's magnetosphere, adding layers of complexity to this cosmic weather system. Saturn, with its elegant rings, also boasts a strong magnetic field. Picture its poles glowing with auroras, similar to Earth's, but shaped by the unique makeup of its atmosphere, mostly hydrogen and helium, with clouds of ammonia. These auroras respond to solar activity and Saturn's own internal processes, a shimmering dance of light in the far reaches of our solar system. Moving still farther, beyond Uranus and Neptune, the cold ice giants present even more mysteries. Their magnetic fields are tilted and offset from their centers, creating bizarre and variable space weather environments. Imagine the wild, supersonic winds in Neptune's atmosphere, influenced by distant solar storms, and the faint, ghostly auroras flickering near its poles. Finally, at the edge of our solar system lies the heliopause, the boundary where the solar wind's influence yields to the vast interstellar medium. Here, space weather takes on a new form, mingling with particles and fields from other stars. Voyager 1 and Voyager 2 spacecraft have ventured beyond this frontier, sending back whispers from the edge of our sun's realm. As you reflect on this grand tour, consider how every planet and moon experiences the sun's breath, in unique ways, sometimes protective, sometimes destructive, always shaping their environments. Picture a sudden burst of energy on the sun's surface, a solar flare releasing an intense flash of light and radiation across the solar system. Almost instantly, this light-speed flash reaches Earth, shaking our ionosphere and briefly disrupting radio signals. But that's only the start. Minutes or hours later, a massive cloud of charged particles called a coronal mass ejection, or CME, erupts from the sun, hurtling through space at millions of miles per hour. Imagine this CME as a giant cosmic tsunami, a dense wave of plasma and magnetic fields barreling outward, pushing aside the steady solar wind like a storm front. As this storm front races toward Earth, it stretches and compresses our magnetosphere. The bow shock ripples with energy, and the trapped particles in the Van Allen belts surge. Magnetic field lines reconnect and snap, releasing bursts of energy that cascade toward the poles. When the CME's charged particles slam into the upper atmosphere near the poles, they ignite the auroras, the shimmering curtains of green, red, and purple light that dance in the night sky. But these beautiful displays are just the visible signs of a far more powerful process, a cosmic dialogue between the Sun and Earth. Now imagine the same CME continuing past Earth, racing deeper into the solar system. It crashes into Mars's thin atmosphere, stirring weak auroras and churning up dust storms. Farther out, it strikes Jupiter's massive magnetosphere, sparking intense auroral storms many times stronger than Earth's. Every planet with a magnetic field responds uniquely, shaped by its size, atmosphere, and distance from the Sun. These storms ripple through space like a chain reaction, a cosmic pulse connecting every world in the solar system. Back near Earth, these solar storms pose challenges and risks. Satellites can be damaged by high-energy particles, causing malfunctions or complete failures. GPS signals become unreliable, affecting navigation on land, sea, and air. Power grids can suffer surges that lead to widespread blackouts. Astronauts in space face increased radiation exposure, requiring careful monitoring and protective measures. Scientists watch the Sun continuously using a fleet of spacecraft positioned around the solar system like the Solar and Heliospheric Observatory, SOHO, the Parker Solar Probe, and the DS-COVA satellite at the Earth-Sun Lone Point. These observatories provide early warnings, allowing us to prepare for incoming storms. Imagine a day when a massive CME is detected heading toward Earth. Space weather forecasters spring into action, alerting power companies, airlines, and satellite operators. Flights may be rerouted away from polar routes, power grids are protected, and astronauts secure themselves in shielded areas. These precautions minimize damage and keep people safe. Space weather reminds us that our Sun is not a static star but a dynamic, living force whose moods shape the very environment of our solar system. Understanding these forces is not just a scientific pursuit, but a necessity for our technology-dependent civilization and our future in space exploration. Imagine yourself floating just above Earth's atmosphere, surrounded by satellites silently circling our planet. These machines are our eyes and ears in space, tirelessly watching the Sun and solar wind. Picture one such satellite, its solar panels unfurled like delicate wings, capturing sunlight, while its instruments measure invisible particles streaming from the Sun. One day, this satellite detects something unusual. A sunspot region on the Sun's surface suddenly flares bright, a colossal explosion releasing light and energy across the solar system. This flare sends waves of radiation hurtling toward Earth, arriving in mere minutes, shaking the delicate layers of our upper atmosphere and briefly interfering with radio communications. But that's just the opening act. Within the next day, a massive cloud of plasma billions of tons of charged particles launched into space in what scientists call a coronal mass ejection, or CME. Imagine this CME as a tsunami in space, an enormous bubble of electrified gas racing at millions of miles per hour, crashing into the steady stream of solar wind. As this storm approaches Earth, it slams into the magnetosphere, invisible magnetic shield protecting our planet. Feel the invisible force fields bend and buckle under this pressure, magnetic lines reconnecting and snapping in a cosmic dance that releases powerful bursts of energy. These energy bursts funnel charged particles down the magnetic field lines toward the poles. Now, look up to the northern skies. The auroras begin their graceful dance curtains of shimmering green, pink, and violet flowing and flickering in a silent symphony of light. These lights are not just beautiful but the signature of an energetic conversation between the Sun and Earth. Beyond the dazzling display, these storms affect technology. Satellites may temporarily lose signal, GPS systems can become unreliable, and radio waves falter. Power grids, vast networks of electrical wires and transformers stretching across continents, can experience surges. You might recall stories of power blackouts caused by geomagnetic storms, moments when the invisible weather of space grounded entire cities. Consider the challenge astronauts face beyond Earth's protective atmosphere. Outside the magnetosphere, they are exposed to bursts of radiation from solar storms. Shielding and careful timing become matters of life and death. Space weather is a constant factor in planning missions to the Moon, Mars, and beyond. Let's expand this scene. Picture the Martian surface under a solar storm. With only a thin atmosphere and no global magnetic shield, Mars feels these storms deeply. Dust swirls in response, sometimes lifting into planet-wide clouds, and faint auroras flicker at the pole's ghostly echoes of the solar wind's touch. Imagine a future colony on Mars, where settlers watch the red sky darken as a solar storm approaches. They retreat to shelters, shields engage, and communications shift to safe modes. The quiet urgency of space weather is part of daily life there. Drift farther still to Jupiter, the giant among planets. Its magnetic field dwarfs Earth's, stretching millions of miles into space. Jupiter's own moons add to the drama. Io, with its volcanic plumes, injects charged particles into Jupiter's magnetic environment, feeding spectacular auroras that blaze brighter and last longer than Earth's. The magnetosphere around Jupiter traps energetic particles, creating radiation belts so intense they can damage spacecraft. Exploring Jupiter means braving these invisible tempests, a challenge for missions like Juno, which carefully skirts the planet's radiation to gather its secrets. Saturn's rings shimmer as you approach, delicate bands of ice and rock illuminated by the distant sun. Saturn's magnetic field hums with activity, its own auroras painting the poles with subtle light. Though less intense than Jupiter's, Saturn's space weather is a complex interplay of solar influence and internal dynamics. Out past the ice giants Uranus and Neptune, space grows cold and dark. These distant worlds have tilted and offset magnetic fields, creating bizarre and shifting environments. Their auroras are faint, mysterious flickers, whispers of the sun's reach across unimaginable distances. At the edge of the solar system lies the heliopause, a boundary where the solar wind's influence wanes and interstellar space begins. The Voyager spacecraft, now in interstellar space, send back faint signals messages from the frontier, telling us about space weather beyond our sun's domain. As we journeyed together, we've seen how space weather is a cosmic thread weaving through the solar system, connecting star, planet, moon, and human explorer. It is invisible yet powerful, gentle yet capable of fierce storms. It's a story of light and particles, magnetic fields and plasma waves, of ancient forces and modern technology, a story that invites us to listen closely and respect the sun's rhythms. Imagine now you and I sitting side by side, not on Earth but aboard a spacecraft orbiting just outside our planet's protective atmosphere. From this vantage point, the Earth glows blue and white below us, wrapped in a thin veil of atmosphere shimmering with the faint colors of auroras. Above, the sun hangs bright and watchful, its surface bubbling and shifting in a constant dance of magnetic activity. Now, picture the year 1859, a time long before satellites and spacecraft. On a quiet September day, a colossal solar storm erupted, what would later be called the Carrington event. This was one of the most powerful solar storms ever recorded. Sunspots grew darker and larger, magnetic loops twisted and snapped, and suddenly, the Earth was hit by a torrent of charged particles traveling millions of miles. The auroras flared brighter than anyone had ever seen, lighting up skies as far south as the Caribbean. People thought it might be fire or some strange celestial display. Telegraph systems, the cutting-edge technology of the time, were knocked offline, or even shocked operators with electric currents. Telegraph paper caught fire in some cases, wires sparked, and the technology that connected continents faltered under the sun's cosmic tantrum. Imagine how it must have felt to witness this mysterious and terrifying spectacle, with no understanding of what caused it, no satellites to warn people, no systems to prepare. Just the raw power of space weather, reaching down and shaking the world. Fast forward to the mid-20th century, the dawn of the space age. As humans launched satellites and astronauts into orbit, the invisible forces of space weather became an urgent concern. In 1967, a powerful solar storm caused widespread disruptions in satellite operations and radio communications, underscoring the need for constant monitoring. Today, we rely heavily on a complex network of satellites and ground-based instruments to watch the sun's moods. The Solar Dynamics Observatory captures detailed images of solar flares and sunspots. The Parker Solar Probe journeys closer to the sun than any spacecraft before, diving into its outer atmosphere, the corona, to unlock secrets about the solar wind's origins. You might picture the probe speeding through streams of charged particles, measuring the temperature, density, and magnetic fields of the solar atmosphere. Each data point brings us closer to understanding how solar storms form and how to predict them better. Now, think about the practical side of space weather in our daily lives. GPS, those tiny satellites helping us navigate roads, flights, and seas, depend on signals that can be disrupted by solar activity. Airline flights that cross polar regions sometimes change routes to avoid increased radiation during storms. Power grids, spanning cities and countries, install protective measures to guard against geomagnetic storms that can induce dangerous currents in their wires. Even our future ambitions to explore the Moon and Mars depend on understanding space weather. The Moon has no atmosphere or magnetic field to shield visitors from the Sun's energetic particles. Mars, with its thin atmosphere and weak magnetic patches, offers only partial protection. Astronauts venturing there will need habitats fortified against radiation and accurate forecasts to time spacewalks safely. Imagine standing on the surface of Mars, watching the sky glow faintly with aurora's ghostly reminders that the sun's breath reaches even this distant world. You feel the cold, the thin air, and the invisible rain of particles streaming by. Space weather here isn't just a scientific curiosity, it's a vital factor for survival. Back on Earth, researchers develop sophisticated models to simulate solar storms and their impact on the magnetosphere and atmosphere. They use these models to predict how a CME might distort Earth's magnetic field, helping power companies and communication networks prepare for potential disruptions. Think about how this knowledge grows every day, expanding our ability to coexist with the sun's powerful presence. Space weather connects us to the sun in an intimate, dynamic relationship. It reminds us that we live in a vast system, where invisible forces ripple across billions of miles. As you and I continue this voyage together, the story of space weather unfolds like a living tapestry woven from light and particles, magnetic fields and solar storms, history and future. Picture yourself drifting slowly away from Earth, past the bright blue marble and its shimmering atmosphere. The sun's solar wind pulses outward, a steady stream of charged particles racing through the emptiness at hundreds of miles per second. These particles don't just vanish after leaving Earth's neighborhood. Instead, they race on to meet other worlds, each with its own magnetic shield, atmosphere, or bare rocky surface. As we glide past the Moon, imagine how it feels to be there, a silent, airless place, where the solar wind hits directly. Unlike Earth, the Moon lacks a global magnetic field to deflect these charged particles. Instead, the surface bears the marks of constant bombardment. Over billions of years, solar particles have weathered the lunar soil, creating a layer of tiny, sharp-edged dust grains called lunar regolith. Each grain tells a story of space weather's relentless touch. Now, drift further out to Mars. Mars has a thin atmosphere and scattered patches of magnetic fields, remnants from a time when its global field faded away. Here, the solar wind sculpts the atmosphere, stripping it slowly into space. Imagine the solar wind as a gentle but persistent sculptor, peeling away gases and shaping the planet's environment over eons. This slow erosion helped turn Mars into the cold, dry world we see today. Farther out, giant planets like Jupiter and Saturn stand as colossal guardians with powerful magnetic fields millions of times stronger than Earth's. These magnetic fields capture and trap solar wind particles, creating vast, glowing auroras at their poles. Imagine standing near Jupiter's poles, watching sheets of green and purple light ripple across thick, swirling clouds of hydrogen and helium. Each planet's magnetosphere acts like a giant bubble, protecting the planet from the solar wind's fury, but also creating dynamic and beautiful light shows. On Saturn, the auroras shimmer in hues of pale green and blue, dancing across its methane-rich atmosphere, visible even from great distances. Beyond the gas giants lie Uranus and Neptune, more mysterious and distant. Their magnetic fields are tilted and offset in strange ways, creating unusual auroras and interactions with the solar wind. Picture Neptune's faint blue glow, occasionally flickering with hidden auroras in the depths of its atmosphere. As we move toward the edge of the solar system, the solar wind slows and meets the interstellar medium, a thin, cold sea of gas and dust that fills the space between stars. This boundary, called the heliopause, is where the sun's influence wanes and the galaxies begins. Imagine the Voyager spacecraft, now beyond this boundary, sending back whispers from the edge of our solar system. Space weather there is a mix of solar wind particles and cosmic rays from distant stars, a blending of two cosmic forces. In this vast, quiet borderland, space weather takes on a new character. It's no longer just the sun's storm, but a cosmic dance involving the galaxy itself. Feel the enormity of it all, particles racing across billions of miles, invisible winds shaping worlds, light and energy flowing through the vast emptiness between stars. Picture drifting closer to Jupiter now, the giant of the solar system. Jupiter's magnetic field is colossal, stretching millions of miles into space, far beyond the planet itself. This magnetic bubble captures charged particles swept up by the solar wind, creating a vast, invisible shield around the planet. Imagine the particles trapped inside, spiraling along magnetic field lines like cosmic dancers caught in an invisible whirlpool. Within this magnetic cocoon, charged particles collide with Jupiter's upper atmosphere near its poles, igniting magnificent auroras. Unlike Earth's delicate greens and purples, Jupiter's auroras blaze with intense ultraviolet light and energetic X-rays, invisible to our eyes but dazzling when captured by special instruments. If you could stand there, you'd feel a pulsing energy, a constant storm of particles crashing into the atmosphere. Jupiter's volcanic moon, Io, adds fuel to this cosmic fire. Imagine huge plumes of sulfur and volcanic gases erupting from Io's surface, injecting charged particles into Jupiter's magnetosphere. These particles become trapped, intensifying the auroras and creating intense radiation belts around the planet. It's a wild, chaotic place, a cosmic light show fueled by the interaction of moons, magnetic fields, and the solar wind. Now, let's glide over to Saturn. Its magnetic field is quieter than Jupiter's, but still enormous and powerful. The rings of Saturn, made of countless icy particles, shimmer under the sun's gentle touch. Here, space weather sculpts the rings, bombarding the icy surfaces with charged particles and sunlight. Imagine tiny electric currents flowing through the rings, whispering secrets of the solar wind's reach. Saturn's auroras paint the polar skies with soft glows, occasionally brightening in response to solar storms that began millions of miles away. These auroras are like distant echoes of solar activity, faint but beautiful reminders that even here, at the outer edges of the solar system, the sun's breath is felt. Farther out, Uranus presents a curious case. Its magnetic field is tilted on its side, offset from its center. This unusual geometry means the solar wind interacts with Uranus in complex and shifting ways. Picture the solar wind flowing unevenly over the planet's tilted magnetosphere, creating auroras that flicker unpredictably. The result is a space weather dance unlike any other in the solar system. Neptune, the farthest giant, is similarly enigmatic. Its magnetic field is also offset and tilted, creating auroras that are faint but present. Imagine Neptune's blue atmosphere, occasionally flickering with the soft glow of auroras as charged particles from the solar wind ripple through its magnetic field. Beyond Neptune lies the Kuiper Belt, a distant region filled with icy bodies and dwarf planets like Pluto. Here, the solar wind grows thinner and weaker but still sweeps through this icy frontier. Imagine the slow, steady brushing of solar particles against these frozen worlds, shaping their surfaces over billions of years. Finally, we reach the heliopause, the edge of the sun's influence. Beyond this invisible boundary, the interstellar medium flow-san ocean of gas and dust that fills our galaxy. Here, solar wind particles slow, collide, and mingle with cosmic rays and matter from distant stars. Imagine standing at the edge of this cosmic frontier, feeling the gentle push and pull of two vast forces meeting in a silent balance. The sun's breath fades, and the galaxy's vast winds begin. This boundary isn't static. It shifts and fluctuates, responding to solar cycles and galactic conditions. Space weather here is a complex symphony of energies, particles, and magnetic fields, a grand cosmic meeting point. And so, our journey through space weather reveals a universe alive with invisible forces, shaping planets, moons, and the very fabric of space itself. From the fiery heart of the sun to the quiet edges of the heliosphere, space weather is a constant, powerful presence. Imagine now that we're gliding past the outer reaches of the Kuiper Belt, that distant, icy realm filled with tiny worlds like Pluto, Eris, and countless frozen bodies spinning silently in the dark. The solar wind here is thin, almost a whisper compared to its fierce gusts closer to the sun, but it still flows steadily outward. Even here, space weather sculpts these ancient surfaces. Particles from the sun slowly erode, charge, and coat the ice and rock, giving these worlds a faint glow in ultraviolet light, invisible to our eyes but telling a story of slow transformation. Now, picture the solar wind approaching the boundary where our sun's influence gives way to the galaxies. This region, the heliopause, is a frontier unlike any other, a cosmic skin where the solar wind's outward push meets the vast interstellar medium flowing in from beyond. Imagine two invisible rivers of particles colliding softly, mixing, and creating waves and turbulence, unseen by us but vital in shaping the cosmic environment. Beyond this boundary lies interstellar space, a realm filled with cosmic rays, ancient particles accelerated by distant supernovae and other energetic events. These cosmic rays are much faster and more energetic than the particles from our sun. As they pass into the heliosphere, they mingle with solar particles, creating a complex and ever-changing space weather environment. Imagine the Voyager spacecraft, now thousands of miles beyond the heliopause, sending back faint signals to Earth. These tiny robotic travelers witness the universe's edge firsthand, feeling the push and pull of space weather from two vastly different sources, the sun and the galaxy. From their distant vantage point, space weather becomes a cosmic dance between stars, a vast conversation across the universe. Turning our gaze back inward, let's explore how space weather shapes the delicate environment of comets. Picture a comet plunging into the inner solar system, its icy surface warmed by the sun's light. As it nears, the solar wind begins to strip gases from its surface, creating a glowing coma and a spectacular tail streaming millions of miles behind it. This tail, made of charged particles pushed by the solar wind, dances and twists like a cosmic streamer, a visible sign of space weather in action. Each comet's tail tells a story of the sun's influence, a dynamic interaction between solar particles and the comet's frozen core. These tails don't point backward simply because the comet is moving forward. They align with the invisible wind of charged particles flowing relentlessly outward. Imagine watching this cosmic breeze shape the comet's glowing veil as it races through space. Now, let's venture to the realm of asteroids, the rocky leftovers from our solar system's formation. Although asteroids lack atmospheres and strong magnetic fields, they too feel the sun's influence. Solar radiation and particles slowly wear down their surfaces, creating a process called space weathering. Over millions of years, this changes their color, texture, and reflectivity, slowly altering these ancient rocks. Imagine running your fingers over the rough, weathered surface of an asteroid. Every grain tells a story of exposure to the sun's breath, bombardment by particles, and the passage of time. This subtle but constant weathering shapes the surfaces of asteroids, making each one unique. As we continue, think about the magnetic bubbles created by planets and moons that do have magnetic fields. Each magnetosphere acts as a shield, protecting its world from the solar wind's charged particles but also creating regions of trapped radiation and complex particle movements. These invisible bubbles vary greatly from the enormous, powerful magnetosphere of Jupiter, which extends well beyond the orbits of its moons, to the smaller, irregular fields around Mercury and some moons like Ganymede. Inside these magnetic bubbles, particles spiral along magnetic field lines, sometimes crashing into the upper atmosphere and creating dazzling auroras. Imagine standing beneath such an aurora on a distant world, soft curtains of light dancing silently in a foreign sky, painting the darkness with colors both familiar and strange. Let's also consider how space weather affects the tiny dust particles and plasma that fill the solar system, forming a tenuous medium known as the solar wind plasma. This plasma carries magnetic fields and energy outward, influencing the shape and behavior of planetary magnetospheres, comet tails, and even the delicate structures of the heliosphere itself. Imagine a vast, invisible ocean of charged particles and magnetic fields flowing outward, bending and twisting in response to the sun's changing moods. This ocean connects every planet, moon, comet, and spacecraft, an unseen thread weaving the solar system together. Space weather also plays a role in the behavior of planetary atmospheres beyond Earth. For example, on Venus, with its dense, swirling clouds of carbon dioxide and sulfuric acid, solar particles interact with the upper atmosphere in complex ways, stripping away lighter gases and shaping atmospheric escape. Mars, as we mentioned, has lost much of its atmosphere due to the solar wind's persistent stripping, a slow process that turned it into the cold desert we see today. Even the giant planet's atmospheres respond to space weather. Jupiter's storms and auroras are energized by particles funneled along magnetic field lines, while Saturn's hexagonal storm at its north pole might be influenced subtly by interactions between solar wind and magnetospheric dynamics. As we look outward, it becomes clear that space weather is not just a phenomenon limited to Earth. It's a cosmic force, shaping the entire solar system, molding worlds, lighting up skies, and carrying energy across unimaginable distances. As our journey through the vast and invisible currents of space weather comes to a close, take a moment to feel the enormity of what we've explored. From the blazing heart of the sun, sending waves of energy across billions of miles, to the distant edges of the solar system, where the sun's breath meets the galaxy's own, space weather is a quiet, powerful force shaping everything it touches. It's the cosmic wind that sculpts planets and comets, ignites dazzling auroras on alien skies, and tests the limits of human technology and exploration. Though invisible to our eyes, it is a living presencer, constant flow of energy and particles that binds the solar system together in a delicate, ever-changing dance. As we look up into the night sky, the faint glow of distant stars and planets holds stories written by this invisible wind, stories of storms and calm, destruction and creation, chaos and harmony. And in the midst of it all, we are observers and participants, learning to read the sun's signals, protect our fragile technologies, and dream of new horizons beyond our world. Space weather reminds us that we live in a universe alive with movement and mystery, where even the emptiness between stars is filled with invisible forces shaping the fate of worlds. Thank you for joining me on this journey. Until next time, keep looking up. The cosmos is always whispering its secrets.